Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturail.it/Jedi. I direct the actuarial program at Illinois State University. Its website can be found at smarturail.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturail.it/help ISU Actuary. This is problem number 3 from the multiple choice section of the recent exam MLC. You are given the following Markov chain model. The annual transition probabilities between the states healthy, sick, and dead of an organism are as follows. Healthy to healthy 0.64, healthy to sick 0.16, healthy to dead 0.2, sick to healthy 0.36, sick to sick 0.24, sick to dead 0.40, and dead is an absorbing state, so of course if you're dead you stay there. Transitions occur at the end of the year. A population of 1,000 organisms starts in the healthy state. Their future states are independent. Using the normal approximation without the continuity correction, calculate the probability that there will be at least 625 organisms alive, healthy or sick, at the beginning of the third year. So the transition matrix for this discrete Markov process, Markov chain, is 0.64, 0.16, 0.20 in the first row, 0.36, 0.24, and 0.40 in the second row, and 001, and the initial state vector for all of the 1,000 organisms considered is 100. They're all healthy. After 1 year, the state vector is what you get when you take the state vector and multiply it by the transition matrix, which really amounts to just writing out the first row of the matrix, because only the first term in the vector is 1 and the other ones are 0, so zeros cancel out everything. So we get 0.64, 0.16, 0.20, and then we multiply that vector by the transition matrix again to get the situation after 2 years at the beginning of the third year. So we multiply 0.64, 0.16, 0.20 by the transition matrix, and we get 0.4672, 0.1408, and 0.3920. This means that an organism that started out healthy at time 0 has a probability of 0.3920 of being dead at the beginning of the third year, and the probability of 1 minus that, or the sum of probability of being healthy plus probability of being sick, and either way it's 0.608, and probability of being alive at the beginning of the third year. Alive being either healthy or sick, but still alive. And we can consider each of the 1,000 organisms starting in the healthy state at time 0 to be a Bernoulli trial with p equal to 0.608 probability of success, and with success defined as being alive at the beginning of the third year. Then the number of organisms alive at the beginning of the third year has the binomial distribution with n equal to 1,000 and p equal to 0.608. So its mean is np, which is 608, and the variance is n times p times 1 minus p, and that is 238.336. And the square root of that, which is 15.4381346 approximately, that is the standard deviation. If we write n for that random variable that counts the number of those successes in 1,000 of Bernoulli trials, then n is a sum of 1,000 independent, identically distributed Bernoulli trials. So by the central limit theorem, it can be approximated by a normal distribution, say W, with the same mean of 608 and standard deviation of the same as n of 15.4381346. And if we write z for a standard normal random variable and phi for its cumulative distribution function, we have I'll show you the calculation, but I want you to note that we intentionally ignore the continuity correction in the process, even though n is discrete and it is being approximated by a continuous random variable, but we were instructed in the problem to ignore the continuity correction. That's why this is happening. So here's that calculation. The probability of n being greater than or equal to 625 is approximately equal to probability of w is greater than or equal to 625. And then we subtract the mean of w, which is 608, divided by standard deviation, and we do the same to the right-hand side. And then we replace this standardized version of w after subtracting its mean dividing by the standard deviation. Well, that is, because w is normal, it has to be standard normal after you standardize it, so it's z. And on the right-hand side, we just need to do the calculation of that, and we get about 1.10 with a little bit of a tail there. Probability that z is greater than or equal to that number. Well, it's 1 minus probability that z is less than that number. And of course, probability of z being less than that is the standard normal cumulative distribution function applied to that number, which we can get either from a calculator of the standard normal distribution or a table. Either way, we get approximately this number. And 1 minus it is approximately 0.13541149. Or some other approximation close to it, hopefully. If you use a table, you will not have as many digits, but it's good the way it is. It's approximately 0.1354. That's answer A. Please remember, this is copyrighted material. The problem comes from a Society of Actuaries, and it belongs to a Society of Actuaries. It's reproduced with permission, but the solution is mine. Good luck in your studies, and good luck on the test.